Okay, let's get started for our talk for today. So today, well, in chapter 5, AC analysis, I have one more problem that I want to cover. But before I get into that problem, I want to cover the theory behind AC power. Now, AC power in our book is a subsection of chapter 5, which is chapter 5.5. Hence the title, well, not title, sorry, hence the number of this chapter. So that's not the right one. That's the right one. Okay, so power in AC circuits, right? Hence the number chapter 5.5. It's a subsection of chapter 5 in our textbook, so I use the same convention. Now, why does AC power matter? And why does AC power matter? Well, we are familiar with the equations and the concept of DC power, right? When you have a DC voltage or current being applied to a resistive load or an inductive load or a capacitive load, energy is being transferred. In case of the resistor receives the energy and then dissipates it in the form of heat, right? With the inductor and capacitor, they are energy storage devices. So if you apply DC, the inductors and capacitors receive the energy, they store it, and they release it back into the circuit at a later point in time. We studied that in chapters 3 and 4. When it comes to AC, well, AC circuits or AC sources basically go in one direction, meaning the positive value in one half cycle, and go in the other direction, meaning have a negative value in the other half cycle, right? Each cycle is equal to each other. So in terms of an inductor and a capacitor in a circuit, if you apply AC voltage and AC current, what happens? In one half cycle, the energy flows into the inductor. In the second half cycle, it flows out, right? AC is basically electrons moving back and forth. When it moves forward, it's positive. When it moves back, it's negative. So in the positive half cycle, inductor receives the energy. Negative half cycle, it gives it back. In an ideal inductor or an ideal system, there would not be any loss, meaning if it receives 1 unit of energy, it's going to transfer 1 unit of energy back. Okay. Capacitor works the exact same way, except that a capacitor is a dual and opposite of the inductor, meaning when the inductor actually receives the energy, capacitor behaves the opposite. Capacitor actually sends the energy out. So in the same half cycle, if a inductor is sending the energy out, capacitor is actually receiving the energy. And this is very important because of a technique that we will use later on in this chapter. That technique is known as power factor correction, or the process is known as power factor correction. We'll talk about it in just a little bit. But why does it matter? Why does this energy exchange matter, right? So to give you a brief overview, electrical power is transmitted over long distances. You're all familiar with these kind of structures, right? Power transmission lines. If you drive through slow, you're able to see this. There are transmission lines that are crossing the regular streets, like on Broad Avenue or Broad Street, right in front of the DMV office. There's a very weird traffic signal. It's right in front of the traffic signal. It's in the middle of the street. Okay. If you go to the shopping plaza at Madonna, near Madonna Shopping Plaza, Sprouts parking lot, I didn't even realize it until like 3 months after I was, after I moved here. I parked my car, and then one day I looked up, and there's like right next to my car, there's this huge structure, and I realized it is basically a power transmission line running through the parking lot. So these actually are 3-phase lines that carry electrical power, meaning electrical voltage and current, or long distances from the utility company all the way into towns and cities, going into residential and industrial customers. Okay. These run to a distribution station. That distribution station is going to take those 3 phases and divide them into, well, depending on the usage. If it's going to industrial customers, they require 3-phase power. If it's going to residential customers, we require single phase, which is what we have coming into our residences and basically our workplaces. Now, this flows from the utility company to the customer, right? When I say flow, I mean it is traveling over these lines over very long distances. Okay, very long distances. Now, chapter 1. When you have electrons flowing in a material, we say it is conducting electrons or conducting electricity. Hence, this is known as a conductor. But, an ideal conductor will have R equal to 0. But a real life conductor will have some resistance. That resistance is given by rho L or A, where rho is the material property. This is for informational purposes. I'm not going to test students, but this is something that students should be aware of. R, the resistance of a particular piece of material, is given by this equation, rho, R-H-O Greek letter, times L or A. A is the cross-sectional area of this conductor, which is basically this, the shaded portion. So the cross-sectional area is basically A. And length, well, of course, length is however long the line is or the cable is. So any piece of wire will have some resistance, and that resistance depends on this equation. Resistivity, rho, is a material property. It's a material property. The ability to allow easy passage or easy conduction of electrons, meaning is it has high, excuse me, it has high current carrying capability, and hence we call it a conductor. The opposite, then it's an insulator, right? It does not allow passage of currents. Anyway, coming back to this, typical wires and cables like these, they also have some resistance, but the length is very small, 3 feet, 10 feet, 25 feet, okay, very small. If you take, for instance, an HDMI cable running from, let's say, a laptop to your TV. Typically, it's about 3 feet, 6 feet, at the most, maybe 10 feet, not much more than that. That cable inherently has a resistance, inductance, and capacitance, okay? But the value of the resistance, inductance, and capacitance is not enough to disrupt the transmission of the signal. But when you have long distance transmission lines that run into hundreds or thousands of miles, the L is large enough that the resistance starts to affect the power transmission through the transmission lines. And so what happens is these conductors get hot, and well, when I say hot, it's not like they are burning hot, but they are dissipating heat. So power is lost during transmission. So every time the utility company sends electricity from the utility company to its consumers, power is lost during transmission. This power loss is also known as I square R loss, because again, power is V square over R or I square times R, directly proportional to the squared of the current and directly proportional to the resistance, right? This is one of the equations for power. So if the resistance is high, the power is going to be high. You cannot do anything about the length. The distance is what it is, right? And so the resistance can only be controlled by the cross-sectional area of the conductor. Again, there are some device physics that limit because there's a skin effect. You can keep making it bigger and bigger and bigger, but then it becomes very heavy, right? That's one thing. And then there's a skin effect, meaning the current or the electrons do not penetrate into the skin of the conductor. They only travel on the surface. So you can keep making it bigger. It won't make too much of a difference. Anyway, the whole point is long distance transmission lines, every time electricity transfers, you have huge losses that occur during transmission. So we don't want those losses, or we want to keep those losses as low as possible. Hence, if you remember, first day of class, I mentioned, right? Our power outlets in North America is 120 volts. Other parts of the world, it's 220, 230, 240 volts. The reason is electrical power is the product of voltage and current. If we keep the current constant and increase the voltage, now we can transmit a lot more power. The whole point is we want to keep our losses low. I square R losses should be low. Does it make sense so far? Okay. So customers for a utility company are broken down into two categories, residential and industrial. Okay, residential and industrial. And the reason is, well, industrial customers have huge electric machines that run constantly, sometimes even 24/7, right? 24/7. There are physical plant, there's physical plant buildings on campus right here where you have electric machines that run constantly. All of these electric machines have a coil winding. Schematically, a coil winding is an inductor. And so all industrial customers have inductive loads. Now, what did we say about inductors and capacitors? They receive the energy and they send it back. Now you can see already why it would be a problem, right? A utility company would have to send power to the customer and then receive it back every half cycle, or sorry, every cycle, right? So the power associated with the inductor and capacitor is termed as reactive power. And the reason is that power for L and C has to do with the reactance. So the power associated with the reactance is termed as reactive power. And it only applies to energy storage elements which have reactance, which is basically inductors and capacitors. It does not apply to a pure resistor. Okay, so resistor does not have any reactive power. Okay, no reactive power. And what happens? Well, the power that is received, let's say for inductive loads, is only used to set up the magnetic field. It does not do any real work. The real work of converting the electrical energy into mechanical energy is associated with what we call as real power, or P. Okay, real power, or P. So to differentiate between the real power P and the reactive power, we use the term Q. So reactive power is noted with the term Q, and it has units of VAR. I have all of this summarized in the next few slides, so it is coming up. If you want to wait to write it down, it's coming up in a couple of slides. And VAR stands for volt ampere reactive, to differentiate it from the real power P. Okay, real power P. So energy storage elements with reactance, meaning only L and C. So when you have huge inductive loads, power is constantly being received from the utility company and then it's being sent back. Now that begs the question, why is it not a concern when it comes to residential customers? So what kind of loads do residential customers have? Look around this room. What do we have? We have lights, electronics, projector. All of this might take up like few hundred watts, right? And if you run it for an hour, maybe it might push to close to like 1,000 perhaps, but not even that. 1,000 watts is 1 unit of power. So in 1 hour, I doubt if you're using that much. Okay, it's just a few hundred watts that we might be using. And most of it is just stationary, right? It's stationary. There's no moving parts. There's no mechanical moving parts except for like perhaps a small fan in there. So in a residential customer, the biggest load would be, any guesses? HVAC, absolutely. Anything else? Microwave is there. Laundry equipment, that's the big one that has a big electric machine in there. So you have a washer and a dryer. But unlike a industrial customer, residential customers are not going to run washer dryers 24/7. At most, you might run it once a week. Now, again, if it's a coin laundry or something, they might have something going on like at least 20 hours a day. But still, compared to an industrial customer, that kind of load is insignificant. It's nothing, essentially. So it does not really matter to a utility company if if residential customers are using like small appliances or large appliances. Those inductive loads do not present as much of a load. Okay, do not present as much of a load. For an industrial customer, it's completely different. They have these electric machines running 24/7, and they are huge, thousands of watts of energy being consumed every hour. So it's a big deal. So the utility company sends all of that power out, right? So here, the power associated with a resistor is P, power associated with the inductor is Q. So total power, P plus Q, is termed as X. And we just refer to it as total complex power, total complex power. So every time the switch flips on at an industrial customer, a utility company has to supply P as well as Q. Okay, P as well as Q. The real power P is consumed to convert the electrical energy into useful mechanical energy. Okay, so the real power P is actually used to convert the electrical energy into useful mechanical energy to make the machine spin and do work, mechanical movement. The reactive power Q is associated with the reactance. It is used only to set up the magnetic fields. So in 1/2 cycle, the electric machines receive the Q or the power, and the other 1/2 cycle, they send it back. So what happens here? You have long distance transmission lines, hundreds of miles long, P plus Q being sent to the customer, and you have Q coming back and forth all the time. 60 hertz, meaning 60 times in 1 second. And every time it travels, you're going to lose a lot of power, lose a lot of energy wasted as heat. And that is why it is a big deal. Yeah, that is why it is a really big deal. And that is why we study AC power. All right, any questions? Is everyone clear on the concept? Okay. So obviously we want to avoid sending Q back and forth all the time, right? Industrial customers have to pay for P, and they also have to pay for Q. Q is charged a nominal rate because, as you will see, we do not have to constantly sending it. We found a way on how to actually avoid that constant travel back and forth. Okay, and residential customers, we only pay for the power we consume, and it's basically this P. Okay, so AC power, yes. DC voltage is in like sending DC voltage. AC is very easy to generate. It's very easy to step up, step down, and transmit over long distances. All of the equipment that we use here in this room is all DC. So every piece of equipment like electronics has an adapter either outside or it's built into the system. So the projector has a AC to DC converter inside it. It's called a rectifier circuit. The laptops, the monitors, the computer, everything has a power supply inside it. 20 years ago, I was playing around with, I was creating like a hobby project with an old laptop, and the laptop was Pentium 100 by Compaq. It actually had a power supply inside it, so you could directly plug it into the wall. So the power, it was like heavy piece of electronic equipment. But the point is everything runs on DC. AC is easy to generate and it's even easier to transmit. So the equations. S is the total complex power. The units are VA, volt ampere. This is very important because you have three different quantities for power. S is the total complex power. Q is the reactive power. It has units of VAR. And P is a real or average power, which we're already familiar with, has units of watts. Okay, units of watts. Now, I will talk about these equations in just a little bit, but think about what it means for a inductor and a capacitor. A resistor behaves exactly the same way for AC as it does for DC. So there is no such thing as impedance of a resistor. It is simply the resistor itself. So if you were to write equations, you would simply write I square times R or V square over R. For inductor and capacitor, you have impedance, ZL and ZC. And they are complex quantities. Mathematical representation is as a complex quantity. And so we do the same thing with electrical power. Electrical power is a complex quantity, and we refer or we represent the reactive power using the imaginary letter J, or the imaginary number J, sorry. Okay, and hence we don't write it as S is equal to P plus Q. We write it in mathematical terms as S is equal to P plus JQ. Now, similar to reactance and impedance, we say that the reactive power is imaginary, but if you ever read that reactive power is imaginary, it is referring to the mathematical representation. Reactive power has a physical basis. Okay, it is real. It has to do with the reactance, so it has a physical basis. It's not just imaginary someone came up with. Okay, it's a mathematical representation which we say is imaginary. So S is P plus JQ. You can see where this is going, right? It's three sides of a right angled triangle in the complex plane. ZL, inductor impedance, has a phase angle of plus 90. So it's pointing up. So plus 90, whereas ZC has a phase angle of minus 90. What is going on? Minus 90, which is pointing down. Right? And so when we plot the reactive power for both the inductor and the capacitor, we get what is known as come on, it's frozen. Okay, and so we get what is known as the power triangle. So for an inductive load, the reactive power QL has a positive 90 plus 90 degree phase angle with the real axis. And QC, this is the positive imaginary axis, negative imaginary axis, and real axis, and this would be minus 90. Again, the same thing, right? Pointing up. If you're going counterclockwise, it's a positive angle. If you're going counterclockwise, it's a negative angle. And so QL has plus 90, QC has minus 90. So you would always plot reactive power for inductor like this, and reactive power for capacitor in the negative direction. And thus you have your power triangle. Real power P is on the real axis, reactive power Q is on the imaginary axis. When you join the two endpoints together, the hypotenuse of the triangle, you get the power triangle. The phase angle theta is known as the power angle. So theta is the power angle. It is also the same as the impedance angle. And the reason is that power angle theta is simply the difference in phase of the voltage and the current, theta V minus theta I, same as the impedance. Same as the impedance. Okay, same as the impedance. This should QL, QC. This is the magnitude of S. Magnitude of S. Okay. Typically, when you have a power triangle like this, we are referring to an entire system. Because if there was just a pure inductor or a pure capacitor in the system, we would only have reactive power. We would not have any real power, right? It would simply be a vertical line on the real axis, I mean, on the imaginary axis. So this is an entire system. So when we talk about the power angle, that power angle most likely will refer to the entire system. Sorry, not most likely. It refers to the entire system, and most likely it would simply refer to the source, because you're taking the entire system into account, the real power required as well as the inductive power. So power angle theta, that's where we come to a term known as the power factor. And power factor is simply the cosine of theta. Again, it is a right angle triangle. So cosine of theta is going to tell you how much reactive power the system requires. Again, it's a right angle triangle. So it's telling you how much reactive power the system requires. If Q requirement is very, very large, then the angle is going to be very, very large, right? Obviously, if Q is like this, angle is 90 degrees, your power factor is going to be cos 90, which is 0. That's the lowest value of a power factor. Okay, lowest value. The highest value is when Q requirement is completely 0. So lowest would be 90 degrees. Highest would be 0 degrees. And cos of 0 is 1. Power factor is written down as a percentage, and it is defined as leading or lagging. Okay, defined as leading or lagging. If the current leads the voltage in a system, then we say power factor is lagging. It signifies an inductive load. Oh, this is capacitive. Ah, come on. Capacitive, and this would be inductive. So typically we would describe a power factor as 89% lagging, 88% lagging. So if a customer tells the utility company that my power factor is about 45% lagging, then it is very, very low. Sorry, not 45. I mean, I was just doing an angle of 45, but if it says 45% lagging, then its cos of theta is 0.45. So theta is cos inverse of 0.45. So that is a very large angle. The utility company will tell the customer that, hey, you need to get your power factor up. Otherwise, I'm not going to send you any electricity. And the reason is when you first flip the switch on, what is going to happen? The utility company sends all of that power to the initial customer, right? The customer receives that inductive power, and it wants to bring that power factor up or the angle down, right? You want to bring that power factor up. You want to reduce this angle. So the way to reduce the angle what is up with this today? It just keeps on freezing. If you have to leave, it's 10 o'clock, you can go ahead and leave. I'm just going to take a few more minutes. Again, power factor, as I said, it's leading or lagging. And the way we bring this down is by connecting a capacitor in parallel with that inductor. So when the switch is first flipped on, the inductor receives the power in the first half cycle. It reaches a steady state. And when the power flows out, it now flows into that local capacitor. So power factor correction seeks to reduce the requirement of inductive power, reduce QL, connect a capacitor in parallel to the inductive load. So once the switch is flipped on, inductive load receives the power in one half cycle, and the next half cycle, when the inductor reaches steady state and is going to send all of that reactive power back to the utility company, the capacitor sort of intercepts and receives all of the energy. So the energy flows from the inductor into the capacitor. And from that point on, when the inductor now requires power in the next half cycle, instead of coming all the way from the utility company, it comes from the capacitor that is local. And so it bounces back and forth locally between the inductor and the capacitor. These capacitors are huge in size. And so that would bring down the power factor requirement, or sorry, the QL requirement. So if QL, let's say, is 4 units, QL is, let's say, 4 units, and you connect a QC of 3, now your total Q requirement is QL minus QC, 4 minus 3, which is 1. You have now brought your angle down. So if QL was like this, and you apply QC in the opposite direction, you're closing the gap. You would never be able to close it 100%, okay, because load fluctuates all the time. But the point is, our requirement is now lower. So instead of, if this was P and this was QL, instead of total requirement being like this, theta 1, you apply QC in this direction, and now your total power requirement, theta 2, is much smaller than theta 1. Okay, 3 minutes over time. Let's stop here for today. And on Wednesday, all we're going to do is solve important problems. Okay, the example 5 in previous chapter, and then continuing on with the power factor correction, and AC power examples in this chapter. So have a good rest of your day, and I'll see you all on Wednesday. Oh, today I won't have any office hours in the afternoon, so I have to be off campus right at 2 o'clock, right after my class ends at 2 o'clock. And so the 2 to 4 office hours are canceled, but I will be available later in the evening via Zoom. If you need to see me, just send me an email. All right. Thank you all.